Yeah, I was trying to have a fun title, but it's actually, you will see through the talk, it's something that we would really like people to think of. In Europe, which the situation might be quite different from Northern America, people are obsessive with not sharing information because that's the root of business. You know, if you don't share, then you're going to do better. And you will see, I can already give you the main conclusion. What I would like us to do is somehow to shift from this paradigm of non-cooperative game theory towards cooperative game theory when it comes to energy. And somehow through the talk, I want to show you why and how. So yes, thank you for the nice introduction, Bisan. So my name is Pierre and I'm a professor at DTU in Denmark. Denmark, maybe you've not been there. It's a country that's doing super well in terms of renewable energy. We love wind energy, so that's why most of the examples when it comes to renewables, it's wind. But most of the things I say you can just transpose to solar, it would do the same. All right, and I'm funded by many projects where we're trying to rethink electricity markets. You have very good electricity markets people also in Canada, so I mean, some of the stuff I'm going to talk about here, and I do. You have some colleagues, I think, in Canada that could tell you similar things. But mainly what's happening through this project and some other initiatives in Europe is that we're trying to really rethink electricity market in a quite disruptive way. What I work on is going towards peer-to-peer markets. So it's quite hyped now. You must have heard about it. People are obsessed with blockchain and some other stuff. But there's some other proposals I want to cover here that are quite disruptive and maybe less hype, actually. So I'll start with a broad audience introduction, and then I have 3 blocks. This one I've removed because I'm going to give an extensive lecture on Friday in London. And if I want to go through all these peer-to-peer electricity markets, it's going to take a while. So I thought I would direct you towards some Matteo, but I will not go through this block here. All right, so the broad audience introduction is that we are all engineers or people into management science, sitting in a business school and so on. And the way we think is always in terms of non-cooperative game theory. So non-cooperative game theory is this idea that I'm going to set up an optimization problem for myself. And if I'm a person having a system view, I believe that if people behave like that and I well design my game or my market or my system, I'm going to get the best out of it, right? And everybody should be happy. But if you think of it, we have a lot of other ways we think of out there. Not as an engineer, not as a business person. And sharing is a part of our life. So maybe you think I sound a bit cheesy here, but sharing is not just sharing as we share a piece of cake in the evening. It's also this new economy, sharing economy that we see through crowdfunding, all these collaborative platforms. In France, for instance, carpooling, you have this BlaBlaCar thing that has become extremely popular. I'm French originally, and I go there like once a year or twice a year. And I remember once, it was 5-6 years ago, I saw an advertisement for BlaBlaCar, and I was laughing. So BlaBlaCar is a system where you can just, if you're driving from one place to the other, you just offer to take people and drive with you, and they have to pay a little bit. And when I saw this advertisement, I thought, I mean, this cannot work. I know France, people just would never do that. And it's a huge hit. And BlaBlaCar works so well. Shared property is also something that's very big. In Denmark, it's very normal to buy a summer house with 3 or 4 friends, and you just share it. Time sharing has been invented in North America, so time sharing, you know what it is. You buy just 1-2 weeks of property somewhere. So we have a lot of sharing in our economy, which is not cheesy. It's real business, right? But there's one thing we never thought we would share, and it's electricity. And now when I say that, normally people are like, well, we are sharing it. Come on, we have shared infrastructures. It's just this constant balance that actually we are all sharing the tension on the grid. The point here is about actively sharing it. So if you have solar panels and you produce extra solar energy, so you cannot self-consume everything, what's happening to your extra power is just going onto the grid. Maybe you get a little money from the system operator or from the state to say thank you, but you're not actively sharing. It's kind of taken away from you and you get a little compensation. So could we share electric energy? Yes, I told you that's the hype right now. People say we could go down to this level and make people share. We have the physical infrastructure. As I was saying, well, some areas of the world are a bit more challenged when it comes to physical infrastructures. But actually, this idea of sharing energy is also supporting new business models for them. So if you think of Eastern Africa or the Central South America, they love this idea that if they design microgrids, for instance now, it would be with this kind of new business models where people feel it's a collaborative venture. So this idea of sharing could actually help some parts of the globe to design infrastructure in another way where it's seen as a bit more of a collaborative game. But mainly what happened lately, oh, it seems my slides are being cut on the right, sorry for that. What happens lately is this IoT. So there's been a lot of work over the last 10 years, I would say, in terms of IoT for smart houses, for electric cars, etc., etc. And then the hype with blockchain over the last few years. So now we really see that we could sense whatever we need, that we have the actuation that we need. And also we could have maybe the negotiating power that we need if we want all these units to communicate and have some kind of market on top of that. All right, maybe what's most important is the system view. Here I was talking about tech and physical enablers. But there is also something happening, and again, I'm not so much aware of the Canadian situation. I think you still have a quite traditional view of the electricity market and system operation. But in Europe, we know we're moving away from this hierarchical view where you would have the suppliers at the top, transmission distribution at the bottom, and all consumers, industrial, residential, in the middle, and these guys at the bottom. Because the system is moving this way. Very decentralized, so you have EVs, you have solar power. In Denmark and other parts of Europe, we also have a lot of micro CHP. So this could be down to the house level or a group of house that share some micro CHP plants. So if we go towards this decentralized system, do we want the markets to evolve that way, right? In a way, yes, but not too much. What would be ideal for most players is that we accept that the system moved towards this physically, but in terms of market, we managed to operate it as if it was still a hierarchical structure, which means that we save the wholesale electricity market, we save all the actors we have in the system, which is a big deal in Europe. I don't know here in Canada if you talk about utilities that might disappear or business models that are not viable anymore for system operators. But yeah, so there's a bit of a dream, you could say, that we could keep the market as it is, and we want to have some new actors, or we want to patch the system. So people say we need a capacity market, it's going to help patching. We need aggregators for demand response, it's going to be a little patch, and so on and so on. But the other way would be to say, let's accept that it's like that, and then we go bottom up, and we rethink the electricity market in view of the new reality, right? And that's why peer-to-peer has gotten quite popular, because if you go peer-to-peer, then you really say, okay, any single entity is a node, is a peer, and we can actually design a market where all these guys interact. And if you do a bit of math, you can say, you can prove mathematically that the pool market as we had is a limiting case of this peer-to-peer market. So it's actually nice because whatever you propose that sounds disruptive is actually more of a generalization of what we had originally. And this is happening in many ways. There's this very nice paper in Nature Energy by a lady called Yael Parra and Benjamin Sovakul, who is a famous energy policy professor in the UK and Denmark. So there they've been reviewing business models, because this is happening in certain countries in Europe, for instance in Holland. And they've been reviewing the different kind of models you may want to think of. So there are models that are full peer-to-peer, which is what people do when they share movies, or there are other ways to think of peer-to-peer. There's this kind of isolated microgrids, and you may think of all these countries with lots of islands. So we have that in Denmark, you have that in Greece. You have also some places where they say they would like to go toward this. So that could be Germany, for instance, with some people who are a bit more environmental extremists, and we say we want to disconnect. I've heard Israel was quite interested also in having this kind of microgrid system. The microgrid can be interconnected, and that would be somewhat a way to make our grid evolve. And the last model would be to have virtual communities. And this is a very interesting idea, because that would mean that these guys here that are connected, it's not because they're connected physically, It's because they want to make an energy cooperative or a group of friends who want to be seen as one by the system. And then within this bubble, they do whatever they want, all right? So they have their own rules for how they share energy, how they share investment, etc. And this is a very nice model because when I talked about this sharing thing, that's what we do somehow. We say if I buy a house with some friends, the house is seen as one by the rest of the system, and we kind of decide on how we're going to share the house, how we pay, how we operate it, how we clean, everything. So there are different models that are being discussed for these virtual energy communities, and there are some countries that have been passing law that are supporting this kind of move, including France, for instance. And there, that's also allow for some new type of business models. There was an example in France of an energy cooperative, for instance, near Montpellier, that was saying, okay, we want to respect and support our local economy. So if we do an energy cooperative, it's to support our local winemaker, right? So the way we share the benefits or the cost for the infrastructure is actually to support our local economy. And there, that's kind of new, because normally energy is just ubiquitous, electric energy. We have it, we use it, and we don't really care. But here, electric energy is part of a bigger picture, right? It's also for something else. All right. Because there's a lot of development, as I say, I'm not going to go into detail. We've been developing this small app. So it's R-Shiny. It's some open source stuff. It's an hyperref link, so when you get the slide, you can click on it. And we would like people to realize what it means if we go peer-to-peer. So here, for instance, it's two villages, two areas in Denmark. And each peer, each node can be producer, consumer, prosumer, whatever you want. They are well defined here. You cannot just change your setup. But then if these people are trading peer-to-peer, you can start introducing product differentiation. So that means that I don't only negotiate with the others in terms of cost, but I might have some other preference. So I prefer to buy more local, I prefer to buy more solar, I prefer to buy with less CO2 emission, I prefer to buy maybe, I don't know, from my mom who live on this other area. And then you could simulate what's happening in terms of exchanges. And you could also think of how new rules for usage of infrastructure or cost for usage of infrastructure might impact the negotiation among actors. All right, so this is something one can play with. And what about the data? I just talked about electric energy, but it seems the title of my talk is about data markets, right? The original proposal that I wrote, so it was 4 years ago, to work on this topic, I didn't want to trade energy peer-to-peer. I wanted to trade data. That was the original idea. And then we thought, okay, it's data for energy, so let's trade data and energy. And then the hype on blockchain came, and then everybody told me, if you say blockchain trade peer-to-peer energy, you're getting the money. So we drifted away from the data. But still, it's in the back of our mind always, and we still do research on that. And there's a reason for it, and that's where we go to the show me your forecast, I'll show you mine. There are many cases where you see there's an interest in sharing information. There's very few papers out there, but intuitively you can think of a lot of cases. And doing the math, you can really prove there's an interest. So we looked at one case here. And this is the case of Denmark or Europe in general. In Europe, we've decided that it's not fair to the actors in the market to not know what's going to happen in terms of renewables, because renewables have such an impact on the market outcomes, right? So the prices are much lower if there's more wind, there's less room for the others to produce, etc. Okay? So this decision from the regulator was to say the system operator is responsible for publishing an aggregate forecast before the market close, sufficiently before, so that people can integrate that in their trading strategy. All right? If you think of it, you are engineers mainly, it's almost like a control problem. You know, you're giving some kind of information to all your assets or your controllers, and this information is going to drive the way they're going to behave. Okay? So what if this information is wrong? And it's a forecast. That means that all the actors are internalizing this information and all doing something wrong, okay? So the beginning of our work was to say maybe it was not a good idea to say we have one forecast for everybody that we share. Maybe the opposite way would be the best, to say, okay, you guys all have your own forecast. You have more diversity of information. Let's make you share information so that you somehow robustly converge towards some form of consensus on what's going to happen, all right? And you could say there's increased resilience. You could say there's motivation for new business models, et cetera, et cetera. So we've shown what was the vicious, you could say, or negative potential impact of having this one aggregate forecast on the market outcome. And then we also discussed what would be the advantage of sharing this kind of forecast. But there's a lot of work on the way, I can tell you, because it's not easy to design markets for information sharing. There are some works in Stanford, in MIT, in Yale, many places, maybe here that I'm not aware of. There's a lady in Toronto also who's looking at stuff that go towards that. So yeah, let's hope we go towards that. But now I want to give you some motivation. We're going to go more technical. And one of the problems where we started with this idea of sharing, it was for distributed learning for renewables, right? So you have a lot of wind farms everywhere. I don't know how much there is in Canada. How many wind farms? How much in terms of megawatt? Do you know?
In entire Canada or just Ontario?
Ontario. Let's talk about Ontario.
I can look.
Okay, but okay, it doesn't come up. Okay, so that's quite big. That's already quite big. Okay, so all these wind farms, what they do is that they do their own forecast. They produce every day their own forecast because they need that to go to the market, to do some maintenance planning, everything, right? All these people, they would like to improve their forecast. I mean, that sounds natural, right? One way to improve the forecast is to get more data, more information. Most likely, who has this information? It's the neighbors, right?
8,400.
8,000, so you have a lot of wind already. Okay, so let's think of all these 8,000 something megawatt of wind. They would like to get information from the others, okay? So that's the premise. Normally, I was telling you when we do wind power forecasting, we gather a weather forecast or data locally. We make our forecast for the next 2 days. In Europe, that would be a classic. It could be shorter lead times, longer lead times, depending on the market. And here, for the example, I'm only going to look at one step ahead, just 1 hour ahead or 15 minutes ahead, whatever. So like if we were in a near real-time market. When we first starting, so it's a long time ago, we worked on that in Denmark. What we've been looking at is what if we could build some kind of spatial temporal model? So we have everybody here sharing data all over Denmark. What would be the benefits in terms of root mean square error? So root mean square error is the kind of lead criterion. And these numbers that you see here is the percentage improvement for a few hours ahead forecast by sharing data, right? So let's assume that everybody here share data. And at the time, the case was realistic because we did it for the system operator, this study. And the system operator can say, well, we've extracted the data from all these people, and we can scramble it around. So we can share data somehow virtually among these people because we control everything. So you see the numbers, you can have 20% improvement. So wind for us comes mainly from the west. So obviously the west side is more seen as a sensor that spreads information to the others, and the guys on the east are beneficiaries, right? But you can see that you get very high improvement, and I can tell you we've not done anything amazing here. It's just simple linear models to start with and see if there's some value in it, okay? So we have a very good improvement, but you need data from the other sides. Okay? All right, so we need data from the other side. Oh yeah, and we'd like to scale it up. So we have a very big data set that's available openly, by the way, on Zenodo. So if you want a big data set for the whole Europe to play with, it is on Zenodo with wind, solar, conventional generators, the network, etc.
Yeah.
Yes?
What is shared? So that's the weather data that is shared or something more?
Here we have wind power, so synthetic observation and forecast. Same for the sun, same for the load. And for the conventional generators, we did reverse engineering, and or there were some public information that we extended, and there is technical and economical characteristics of the generators. The only thing that is missing is the true characteristics of the lines. But since then, there's some other data sets that were published, and if we merge the two, we can have also the true characteristics of all the lines. So that's very good. All right. And so we go to the core of the problem. Do we want to share data or not? Do you want to share data yourself? Do you want to share data? This was the question. Yes, you want to share data? You're so nice. So I worked, I don't know how many years, 16 years I think, I work on this type of problems. The core of the problem that we have all the time is that people don't want to share data, okay? So people don't want to share data. Why? First, because, I don't know, it's cultural. You don't want to share private information. Second, there's no incentive. There's no data market. Maybe if there was a data market, you make a trade-off, a privacy utility, and you start, you know, I'm going to share. But also, no one has ever showed them there was an interest in sharing data, right? So that's where we start. We say there's an interest in sharing data, and now we want to do something for you. So if you don't want to share data, can we share computation? So instead of centralizing the data or you sending me your data, can I write a learning problem that can split, and then I send you a little piece of computation to do for me, and by doing this kind of distributed learning, I could get the same as if we were sharing data. If you do a distributed optimization, you know that we can do that. We can write an optimization problem for learning, we can decompose it, and then I can send some bits of computation to do to different agents. So what the first thought we had, and we presented it in China at a conference in Beijing, was to design this distributed learning setup, where you say, you don't want to share data, okay, but I distribute my learning, and I will pay you a little bit for you do this piece of computation for me. So that's why I call them contracted agents. And people, I contract them, and we have a deal that you're going to do a bit of computation. I'm going to centralize back the computation, and then I'm going to improve my forecast. All right? So this is, and it has to be privacy preserving, because that's the deal. You didn't want to share your data, so I should not be able to figure out what data you have. This is very difficult, by the way, to be truly privacy preserving. So we made a mathematical setup. And so I was the sole author of this paper, the original paper, but since then there's a few Chinese colleagues who picked on it and wrote very nice papers. We wrote other papers with other people, so I think it's building up nicely. But with this idea, you have a central agent, and you could be either a wind farm operator or a portfolio manager, so you have several wind farms. We have a lot of portfolio managers in Europe, you know, that trade for you on your behalf. Or you could be a system operator, so you have the responsibility for all the wind farms in the area. So far, by law, it's obliged to share data with the system operator in Europe, but it might be in the future, if we liberalize further the system operation, it's not really sure what the relationship is going to be, because system operator is not going to be a public entity, maybe. It might be a private business. So we have these three cases. And in the three cases, we can assume that this central agent may want to contract any of these guys around to improve its forecast. So if you do a bit of business, you think of one thing more, is like, oh, who am I going to contract? And I guess I want to contract the minimum number of people as possible to help me improve my forecast. So we have to keep these things in mind. To do it simple, again, we start in the linear case. This can be extended to nonlinear cases, but it's a bit more involved. But we can write simple linear models where this would be the power at my site of interest or group of sites. This is my own explanatory variable, so that can be my past observation of power at my site, some meteorological measurements, etc. These are my coefficients to build a regression. And then on this part, this is the other guys, my contracted agents. So right now, I write it as a centralized problem. So I have all the variables of everybody, all the coefficients, and we can write it as a simple linear regression problem, super easy stuff if you do machine learning or statistical learning. And we're going to use lasso as an estimator. So we have a penalization on the coefficient, and that's for what I was telling you. I want to have it as sparse as possible. Lasso has the effect of trying to have as many as possible of the coefficients to be 0. And for us, if coefficients are 0, it means that on this side, it means that this agent is useless for me. It doesn't bring information, so I don't contract him, right? So that's why we're doing that. And after we've done the estimation, a forecast is very easy to make, again, because it's linear regression. So one can use ADMM. So ADMM should be a famous method for most of you. There's a very highly cited paper by Stephen Boyd in Stanford on ADMM. And I think it's popular because it's very easy to apply, and it has a lot of nice property. ADMM, for instance, has naturally this idea here that you have a supervisory node, a central agent, and this kind of slave nodes. So that's my contracted agent. So we use ADMM for splitting the problem. The original learning problem is like that. I split it in terms of my own design matrix and parameters, and then all these guys are the contracted agents, and they have their own data, their design matrix AI, and they have their own parameters BI. And what I can do then is use this iterative approach of ADMM, where each of the agents is going to do his little bit of computation. As a central agent, I'm going to fuse that, I'm going to merge that with my own stuff. And then you have some kind of a dual update, which is there to drive the process. Okay? So this you can find in my paper or some other papers, how to apply ADMM. And that makes that we get to this level that we can do the distributed learning without sharing the true data, you could say. All right. So I have a little case study to show you how it would work. Two case study, one with data from Australia. So all data in Australia is public. It's very nice. Ontario was doing the same before. I don't know if they still do it. Some of the first data sets I used for wind power competitions were data from Ontario. But yeah, I'm not sure what happened. I think they have stopped. Here in Australia, the data is still public. So even though it's public, the data is of varying quality. You have to be careful. So we built a data set based on this public data with JETRO. Here, and we share this data set. It's with quite a lot of wind farms here over this area of South Australia. Yeah, you have 5-minute resolution data originally because the market in Australia is a 5-minute market, very short-term market. And we've coarsened it to 30 minutes. And then for this work, I was sponsored by EDF in France. So we used their own data set. And the point was exactly that when we got first, so Enedis is the distribution system operator part, and EDF, you know, is the traditional big French power producer and utility. They have a lot of sites over this area, and what they wanted to do is really to be able to design models that would cover a lot of sites at once, and then also that these models would be ready for the future business models they could be. For instance, that people will not share data, right? So that's why we invested originally. We had almost 200 wind farms there. And so we use these two data sets for applying our ideas. The first case I was telling you is having a single wind farm operator. So assume we are in Australia here. I'm at wind farm number 8. I want to improve my forecast, and I'm going to do some distributed learning. So I'm going to start contracting people around, maybe, and I'm going to try to improve my forecast. Yes, so I use very simple models. I will compare against a persistence benchmark. So persistence is that you use the last measurement as your forecast. It's very simple stuff. But when you predict for the next 5 or 30 minutes, it's very difficult to beat, actually. And when, this is the RMSE. If I use persistence, this would be the RMSE value for my 30-minute ahead forecasting. If I use a simple autoregressive model, so that's just with my local data, this would be the score. And when I do distributed learning, so I'm going to contract some agent around, I improve a tiny bit. Again, this is a difficult case. It's a single wind farm. It's very short term. So we're already happy we get an improvement. And side information through the sparsification, we could get improvement here by contracting only 1 or 2 other wind farms. So it's actually quite cheap to get the improvement, but the improvement is tiny, you could tell me. It's still significant. All right, we did it for a lot of wind farms. So it's kind of an analysis over all the wind farms we had in the French data set. Remember, there are 187. So we did it for each and every wind farm, and we looked at what would be the improvement in RMSE, the distribution of improvement, if I was doing distributed learning for all the wind farms. So on average, we would have like 4% improvement. For some, it would go to 10. For some, it would not even be above 0. So it doesn't seem to help, right? But in all cases, it was confirmed also that you only needed to contract 1 or 2 agents to improve your forecast, which seems to be intuitive. I mean, there's strong correlation. So if there's extra information out there, most likely there's correlation among the agents. So if you have information from one, maybe you don't need information from the others, right? There's also this thing I was telling you about weather regime, about weather regimes. These guys who go to 10%, most likely they're on the east side of the park of wind farm, and they use others as sensors. And those who have no improvement, they're on the west coast, and they don't really need the information from the others because the information they would like is from the Atlantic Ocean, right? Okay. Then the portfolio manager, it's a bit more interesting. So it's smoothing the signal. The signal to noise ratio gets better, so you hope you're going to have a higher improvement when you get some data from others. We use the same methodology. We have local models only. We have a persistence benchmark because people always want a simple benchmark, and then the distributed learning. So you see here where I've made a simple portfolio. I took 8 wind farms in the French data set, randomly chosen, and then I want to do distributed learning. So the AR model, so local information only, does a bit more better than persistence. And then by doing distributed learning, I improve by 15%. So that starts to be a bit sizable, right? And in terms of market participation, if you improve your forecast by 15%, you're going to save a bit of money, I can tell you. Same story, because we have this L1 penalization, I still don't need to contract many people. Here again, I was contracting 2 or 3 other agents in the whole park of wind farm of nearly 200, and I would get this kind of improvement. So it's really strategically picking these guys. We've also made some studies as a function of portfolio size, wind farm distribution, etc., but it's a bit long and boring to go through that. In the case of the system operator, it's the limiting case that you consider all the wind farms, all the cases, all the sites. Here, I don't remember why, but we didn't use the whole set of wind farm. I forgot why, but we use a bit less than 100 for this case. I think, yeah, in this case, it's because of data quality issues. We wanted to be sure that over the whole periods we considered, we had 100% of the data available, so that there's no spurious results because you're missing data at site. That was why. So there were only 85 of these 200 wind farms that had continuous data records over the period. All right. Same story, if we use only an AR model, so it's a simple linear regression with your own data, we would do, we do quite better than persistence. And then we're going to improve a bit more by doing the distributed learning. In this case, you see the improvements are not amazing, but it is a limiting case. We have the system operator somehow is covering the whole area, so all the wind farm together, remember, here. All the wind farm together. So the system operator, when it does its own model, is working on an aggregate of all this wind farm, which is a smoothing of all this data together, right? So the signal to noise ratio is much better, and somehow it's already including the information from all the wind farms, right? Well, in this case, what you add is only data from these 3, and you would like to have data from others to improve, all right? So it's normal that in this case, somehow it's just a distributed version of the same problem. You don't add extra information, okay? While here you add extra information, and here you add extra information. Right, so at the end of the day, we saw that we had little improvements. If we do it for a single wind farm, you can get lots of improvement if you do it for a portfolio. And here the improvements are not amazing, but you had the advantage that there's no data sharing, all right? So that's why originally our idea was to say, okay, we could start with this. Instead of doing this business of peer-to-peer for energy, maybe we could set up a market platform so that people do distributed learning, and you would pay a little bit for everybody that helps you improve the forecast, all right? And then we could push it to selling data. Selling data is another story. Okay, but are there reasons why we would like to do that and to push it further? I want to show you 2 examples which are about uncertainty and variability. How good are you with renewables in electricity market in general? Average? Average plus? Okay. So, but then I'm going to start with 2 statements, right? It's very nice to have renewables in electricity markets because it's helping with our sustainability goals. But at the same time, it's also a bit challenging because they bring uncertainty and variability, right? So that's a whole course in a nutshell. Uncertainty is because when you go into the market, it's a forward mechanism. So you have to tell in advance what you're going to supply, right? So there's going to be a block of energy. Typically for us, it's an hour. Here, I think you have shorter time range. So maybe it's blocks over 15 minutes or 13 minutes. I forgot how it is in Ontario. And so you use a forecast, and you say, okay, this is the block of energy I'm going to supply. and obviously your forecast is wrong. So what you're really supplying is this, right? So there's the difference between the block of energy you offer and what you really supply. So that's the uncertainty issue, and that yields energy-related regulation costs, because in terms of energy, you deviate between your contract and what you really deliver. We already have mechanisms for that. That's the balancing mechanisms. So you could say this is already covered. Still, it can be improved. We'll discuss it. Then there's variability. You can imagine that if I trade a block of energy over an hourly period with my wind farm, it's quite likely that I'm not going to deliver something like that, right? So when I offer a block of energy, if it's a conventional generator, there's an implicit understanding you're going to do it with a flat power profile. With a wind farm, if you make this assumption, I think it's not going to go so well. So what you're going to deliver is this, right? It's some kind of funny profile. And it's something we accepted. I mean, since the beginning, somehow if you want the grid codes, I've said, okay, you have to deliver at constant power profile unless you're a renewable energy generator, because you cannot really do it unless you have batteries or demand response, but then it's super expensive for now. So that's what's going to happen. And there, you're going to need primary and secondary reserve. So it's other generators who kick in and counterbalance these fluctuations, okay? So that brings energy, possibly, through integration of this profile, and power-related regulation cost, because it's in terms of power that you're going to have to follow this profile. All right? Okay, so who's paying for that today? When I go to the market with a wind farm, and there's energy and power-related regulation cost, because of me, do you know who pays? You sure? I mean, I told you for this part, we have a balancing market. So you have some kind of a contract with the system that you're supposed to deliver this. So if you deliver that only, you're going to have to pay for the difference. You're going to cover yourself. So as an agent, a wind farm producer, you're financially responsible for this deviation, okay? So for this part, already now, the system covers you as an agent, you have to cover the cost. But this, you're totally right. This is passed on to the consumer. It's all socialized, because we say, damn, it's too complicated to do that, to really pinpoint at people and saying, it's your fault, it's your fault, it's your fault. So for this part, this is socialized. And as an agent, you're like, I don't care, you know. I just deliver, and they'll figure it out. If you're a system with a lot of wind and solar, the problem is that these costs are not negligible anymore. When they were negligible, you say, okay, we pass it on to the customer, the final consumer, it's okay. But as they grow and they grow, it's not really acceptable. If you think of history, it was the same for this part. Originally, and I think Canada was also like that until recently, wind farm would go into the market not being responsible for deviation from their schedule. They would be forced to give a forecast, but they would not pay for the deviation between what they forecasted and what really happened. Why? Because they say, okay, we have to support wind farms. If we start penalizing them all the time, they are not going to invest in wind farms, these nice people, right? But at some point, the cost is not negligible, and you want to incentivize having good forecast, and you want to incentivize also a good behavior in design, business cases maybe for storage, so that you minimize this thing. So we've already moved towards sharing the cost of that among the relevant players, and we've not done that yet. Same story, it's political. You don't want to over-penalize the wind farms and the solar power plants. But as the cost is non-negligible, we're going to have to go there, right? Okay, so we want to change the way the market is designed. And what some people have proposed is actually to merge the trading floors. So you have a trading floor here, that's your forward floor. But then you would have another floor here in real time, which would be for settling the imbalances, so the differences, right? You could integrate it. So the way, what we call conventional here, conv-D, is the sequential as we have today with deterministic forecast, and you have two optimization problems to solve. You have a MILP for the forward stage, and you have another MILP for the real-time stage. What you could do is you could write it as a stochastic program, so you try to account for the uncertainty for the real-time stage and bring it to the forward stage. And you could also write it as a bi-level program. So that's a bit more of a complicated construct. But that would permit somehow to get the benefit of this and some also of the interesting feature of that. So different people have proposed some of these mechanisms. And there are some very nice properties of these various mechanisms. I don't want to go into too much detail with that. There's a paper here that we have in the Operational Journal of Operations Research, and I think there's been a few follow-up, where we look at the expected costs for the overall system management as a function of wind penetration and some other parameters. So we use this IEEE 24 bus system, which is a classic system for people doing a study in operations and markets. So you have some conventional units, you have some wind farms, we have technical and economical characteristics. And then we look at the total cost of operation in expectation. So integrating the day-ahead and the real-time cost. So you want to cover this uncertainty-related cost as a function, I was saying, of wind power penetration and then correlation between the wind farms, all right? So just to go through the main feature of these plots, here you see as you have more and more wind penetration, you have three markets in parallel, the conventional as we have today, the stochastic, and the bi-level. All the three are together. So somehow, as the system is flexible and easy to manage, whatever the market design, it does the same. You know, the more wind you put in the system, the more you get social welfare increase. The cost of managing the system are lowering because wind is free, and the recourse cost for balancing afterwards are so tiny that you don't mind. So it's going better and better. And you see here that's the conventional. At some point, it's just getting away from this nice tendency, and it's because at some point the cost of the recourse, so having to manage the forecast errors, takes over the benefits in the first go of having more and more wind in the system. So you have this kind of splitting here, all right? But you see that the other two, they still continue to improve system cost, expected system cost. The stochastic program, it's normal because it's kind of the ultimate tool to bring the uncertainty of the real-time stage in the forward mechanism. And that's kind of an ideal benchmark. But a stochastic program doesn't respect some of the features you want for markets. So for instance, it doesn't respect the merit order. The merit order in markets means the cheapest is dispatched first. Then the next cheapest is dispatched second, and so on. A stochastic program doesn't care. A stochastic program say, no, you wanted me to be smart about uncertainty and flexibility, so I'm not going to respect this ordering of dispatch, okay? Which means that if you design a market based on the stochastic program, you may have people entering the market in a loss-making position. Have you ever heard of a market where you get in and you may lose money? No. In a market, if you come to offer a service, you have to be paid. You cannot lose money. So this is not right. What the bi-level setup is doing is blending the two. It is giving you the benefits of a stochastic program because you're bringing the uncertainty in the first stage, but by construction, a bi-level program can enforce you respect the merit order, so no one is in a loss-making position. So that's why you follow the same trend, but you have this little gap, and this little gap is the price to pay to respect economic theory or to respect what people want, you know, that they don't enter a market in a loss-making position. All right, if there's just one message also there, it's this. And as you have a stronger correlation among players, here. Whatever market we have today that is deterministic and sequential has a breaking point. So there's a certain level of wind that you put in the system from which it's not really beneficial anymore. And I think maybe not in Canada, but in Europe, we've heard that a lot of times. There's a maximum amount of renewables we want to put in our system. And it's true, in a way, if you think of the electricity market setup. If you follow the conventional market design from a certain level, so here you see for a certain correlation it's 38%, for another correlation it's 33%, but this point exists. You can prove it mathematically, this point exists. There is this breakdown point. But if you change the market design, you can always get more benefits by having more renewables. So that's a strong incentive for changing market design, right? All right. There's a few open problems. Where does the probabilistic information come from? If we want a stochastic program or a bi-level setup, you need probabilistic information. And the fact that the probabilistic information will never be perfect also. It's like any forecast. You make a forecast, it's never going to be perfect. So we have challenges in market design where we want first people to come with probabilistic information, not the classical block offers that are deterministic. And you want incentives for people to be truthful and look for improving forecasts, all right? So we've designed electricity markets with probabilistic offers. So that's what I was telling you. I mean, there are some ideas that can be a bit disruptive and not so hype. This is one. It would be so cool if we accept that everybody is an uncertain player, you could say, in the system. Why don't they come trading their uncertainty, right? I mean, it's a bit ridiculous that we have a market that is deterministic when everybody in the future will be uncertain. On the demand, they're uncertain. Wind power is uncertain. Solar is uncertain. So how come we have a market that is just with uncertain player? I think I saw 2 weeks ago, there are people from Caltech. They claim they have the first full market design with probabilistic offers, which might be true. I don't think our proposal was totally complete. But still, it's something that is going to happen. I know people in Berkeley working on that. There are people in Caltech, etc. So we have a small letter in a transactional power system you can look at. And I'm not going to go through it, but we've proposed a mechanism where people would make probabilistic offers. So you make a probabilistic forecast and you offer your CDF in the market. It could be an interval also. Then what we did is that the same way you have a congestion rent, we defined an uncertainty rent. So that's a part of the money that's kind of taken for the system operator to book the reserve to cope with this uncertainty. Then the market clearing, you do whatever you want. And at the end, we have a mechanism for attribution of balancing cost. So it's counterbalancing your actual difference in schedule, but also the cost of the uncertainty you brought to the system, all right? So these kind of mechanisms in the future, I wouldn't be surprised if they are proposed more and more. The only thing I can say about that is that regulatory authorities don't like it, and all agents in the system don't like it. And that's our fault, teachers maybe. Engineers and people who come out there, they don't think probabilistically. Economists also don't like to think probabilistically. So all this market design where everything is uncertain, they don't really like it, and they prefer to stick to this deterministic market design. All right. Still, there's this point of the profiles, which is the light point I want to cover. We also wrote a paper you can find. Oh, it's not under review anymore, sorry. I put the footnote, but it was not updated. We wrote this paper with people at EPFL. Jean-Yves Le Boudec is a professor there, and 2 of his postdocs were involved. Our idea was to say, okay, now I've proposed this. That's my forecast for an energy block where I assume flat profile. Obviously, there's a deviation, but there's also a non-flat profile, okay? And I want to generalize the revenue of the producer. Normally, the revenue of the producer, so that's the revenue for producer I. The revenue of the producer I is what you predict times the day-ahead price in the forward market. Then you have this imbalance settlement. So the difference between what you predicted and what you really produced is settled as at a balancing price. But then we add a new piece here, which is most likely a loss due to the variability in your power delivery, okay? So you're going to have your share of cost from not delivering a flat profile. The question now is how we design this term, how we define it, and it has the nice property. Do you have an idea? No idea from the classroom? All right. First of all, we can just add up all the costs, right? If we have, as we do today, we are not really sure who's doing what, but we have an overall cost. So all the costs we have for primary regulation, it comes from this kind of variability from all agents. So if we add up all these costs for primary regulation, we have the overall power regulation cost, okay? So that would be RP. Then we want to share it. So you want to define a metric where you say, I'm going to take a ratio of my own value of the metric over the sum of the value of the metrics of everybody, and that define my share of the total cost to cover. So my RIP, my share of the cost for this power variability is going to be obtained like that. That sounds simplistic, but that's the easiest way to design an attribution rule. So what D should be? There's been a lot of proposals through history for attribution cost. There's some metrics that could be related to capacity. So somehow you look at the maximum deviation here through the hour, and you say, well, it's only fair I use this maximum deviation because the unit, if I think of sizing, the unit I'm going to need for this hour is going to be linked to the maximum deviation, right? So I want to make you pay for your maximum deviation. It's a really tough one because if you're flat, then you do have one spike and you're flat again, you're going to pay a lot, while it was just one instant where you deviate a lot, okay? But still, there are some people who support this idea that it's about capacity. And we already have mechanisms today where there's this kind of capacity metric. I think it's northeastern US. There is some metrics like that that are used for balancing cost. Then you can use integrated mismatch. So you can integrate the difference here. So you're going to take the area here. And then you're going to consider what's my share of the total area of mismatch. All right. Then there could be mileage. And again, mileage is used in PGM because you say if there is a lot of cost related to regulation, and it comes from asking storage. Storage to do this service, storage has some mileage cost, so cycling cost, right? So what we want to do is reflect it here, and maybe we're going to take a norm on some gradients, and that's going to show me somehow how this variability is going up and down all the time, all right? And that will be a mileage cost. And finally, you could consider a more geometric approach, where you see this, if there are, for instance, 100 time step here, you see it as a 100-dimensional vector, and then we're going to make an inner product. So there's my own vector of deviation, the overall vector of deviation, and if I take an inner product between my own contribution and the total contribution, my own deviation and the total deviation, mathematically, actually, it's a very nice way to define contribution because it would have a lot of nice property, so being subadditive, so being additive, non-negative, etc. And in terms of mechanisms, it brings some nice properties. A nice property, for instance, is that if you use this one, you have no incentive to form a coalition with some other players. While if you use this one that are subadditive, then that means that if you team up with someone else, most likely you're going to pay less than if you have to face the cost yourself alone, right? So this kind of incentive for coalition, in general, you don't like it. So the fact here you have no incentive for coalition because it's strictly additive, then it's perfect. There's also the non-negativity is the same as I said earlier. You don't want to have people who could be rewarded maybe for bringing variability to the system. Or maybe you want that. Maybe you think if their variability is helping the system, they should be paid also. But that's quite unlikely. All right. So we had a test case with real data in Denmark. And this test case, we considered the different type of metrics. We have a lot of players. And there's an analysis in the paper. I'm not going to go through it because it can be quite long. But we verified the properties, not nice and nice properties of some of these metrics. We calculated what would be the payments. It's realistic data, so that would show somehow how big is this RIP. And somehow we made a concrete proposal for having this kind of mechanisms. Why we are pushing for that? First, I was telling you we would like people to have a more collaborative approach. So if we could find ways to minimize variability, everybody would benefit, right? If we have this kind of payment, also you have an incentive for demand response and storage. Right now, people say, okay, there's no incentive, nice incentive for demand response. Obviously, if I don't have to pay for the cost of variability, I have no incentive to find a business model to smoothen this variability. So we believe that will help. Though, so the feedback from people in the real world, you could say, is that they are not very keen because this guy is most likely, I say we see this as a revenue, right? So this is positive, and it's quite sizable. This is most likely negative, not so big, but still you're taking away some money from the wind farms. And this one, I told you, by design, we want it to be negative, so we're taking even more money from the wind farms. And so for a system operator, regulatory authorities, and so on, they say, okay, but it looks like we are bashing again the wind farms, so maybe we don't want that. Still, we have this move, you know. First of all, you go for feed-in tariff and no responsibility. Then you take away the feed-in tariff. Then you make them responsible in terms of energy. So why not going all in and make that responsible fully? And really, if there are some technology that can support minimizing this cost, then that would support the business model and everybody's happy, all right? Okay. So as I said, for the peer-to-peer stuff, either you come to London on Friday, or you can pull the string and get the papers that I mentioned there. But I want to conclude now. And yeah, I think I cannot talk for Canada, but I would expect in general, if you look all over the world, that electricity market would also go more decentralized. It's going very strong in Europe right now, and I think it's not only Europe. In Asia, especially China, I think there's a good push for going peer-to-peer, not for the whole system, but still at least for localized markets. In terms of main messages, I think one of the most pressing needs is to really understand the cost that there are for operating the system and the extra costs from renewables, and then to attribute them correctly. And again, peer-to-peer is ideal, because if you decentralize completely, you're sure also that the cost structure is going to be, I would say, pushed also, or the element of the cost structure are going to be a burden for each and every component individually. We have also to accept that everything is uncertain, so all these new mechanisms have to be thought of in a probabilistic framework, which is very difficult. It's clear, but it's needed. So I already talked about this cost. Decentralized market mechanisms, it is actually something that can be also an opportunity. If you think of it, well, again, I don't know the situation in Canada, but the fact that we have in Europe a centralized market and very little payment for the energy you push to the grid makes that a lot of people, when they think of the business case, they say, I'm not going to put solar panels on my roof. But if you have a decentralized market mechanism and your nodes in the market, and maybe for you it's not about the money, it's about sharing the energy with your neighbor, with your mom, or to make a contribution you yourself towards sustainability for the system, maybe you would invest in solar panels, whatever the money you're going to get out of it. Well, if it's really top-down system view, you may not want to invest. So this is not about engineering, it's about a general change of the view of the system and the incentive structure. Think of it of public transport versus private cars, right? The private cars is the peer-to-peer view, and public transport is the centralized top-down. We have the two that coexist, and we seem to be nicely enjoying pushing the barrier a bit more towards public transport or towards cars. Here in North America, you're more towards private cars. In Northern Europe, we're more towards public transport. But still, it's nicely coexisting. So looking forward, one big piece of work we are doing in Europe, and DTU, I think, quite strongly, it's all this idea of generalizing market mechanisms. So we talked today about probabilistic offers, but there are a lot of other ideas that people work on here also in Canada. Rights, that's the thing in the US, you know, there are transmission rights, now they're going to be storage rights, and what we're extending it to is flexibility rights. What we would like also is that since everything is a dynamic system, a stochastic dynamic system, maybe we don't want to trade in terms of blocks, but in terms of control policies. So what you trade with the others is the ability you have to react to how uncertainty is going to unfold. So there's a lot of nice things. But then the key, I was saying, maybe you heard me through the talk about cooperative stuff, additivity, subadditivity, and so on. I think something we're missing, there's very few papers that really look at all these problems in terms of cooperative game theory versus non-cooperative setup. I think we have to rethink that a bit more thoroughly. And this is because, conclusion is, whatever we do in the future, energy through the weather, from the weather is going to be a collaborative common. So we all have assets for getting a bit of energy from the weather, but somehow it's something we all share, right? So we need some kind of fair design for how we're going to share it, and most likely the true cost of harnessing this energy is going to be very low. So it's not about the money, right? It's about having a fair mechanism for we get energy from the weather. And fair is about all the players, but sustainable is about how we're going to behave, all the agents versus the system and the resource, right? So I think this is the main challenge. right now what I discuss, even though, I don't know, maybe it sounds a bit complicated because you're not such experts there, but it's very incremental still. It's very incremental. The real game is to try to think like 30 years ahead. If there's no more marginal cost being non-zero in the system, so everybody has access to free energy, everything is distributed, everything is uncertain, what is the right market design? Do we need a market in the first place, by the way? So this is really the question. So there was Joshua Taylor, I mentioned in Toronto, who wrote a paper about power system without fuels. So there's this idea, you know, there's no more of these traditional fuels. Everything is about wind and solar. And his idea is that it's a pure game theoretical setup, you know. All the agents are just bargaining, trying to make some money to recover the investment cost. But it's this kind of mean-field game, you know. Everybody's playing and stabilizing to some kind of equilibrium. And the price of energy is not a true price. It's just a point of tension between all the players. So there are a lot of interesting ideas. And if you want to work on that, I would be very happy to see some of your papers coming up in the coming few years. Thank you very much.
Any questions for Pierre?
Yeah. So it was a bit longer than what I thought. I said 40 minutes. That was good that time. So we go back to the beginning. Yes?
I'm wondering how you model this kind of data. I mean, this is the spatial temporal data.
Yeah, so here, there is a paper for that. I could give you the paper. What we do is we consider it's 15 zones here, and we consider the processes for each and every zone as one vector. So what's happening is a 15-dimensional vector for every time t. And then we have a model, which is a generalization of this autoregressive model, but with vector processes, right? So we have matrix coefficients that show somehow how the information is shared between the areas. And it's quite simple to write these models, actually.
Yeah, but I have to do some similar stuff like this. But there is many regions.
Yeah.
And then every region, I think every region their period is different. So if we model all these regions, this periods of every region would influence each other.
Yeah.
Right, so.
Yeah. But so after here we have done it. This study was an idealized setup. But after that, you can make it to more general setup. Optimally, if you write it in terms of a continuous process. So if you use stochastic differential equations and partial differential equations, mainly here, you can write it as a continuous process. And then in terms of your discretization, you would be able to consider different resolution for different areas, different amount of available information, different type of dynamics also you may want to couple. So I mean, some of my colleagues at the Applied Math department and myself, we've been trying that. I think it gets very heavy. So it has a lot of benefits, but it has a cost also. But still, there are ways to look at this problem in different ways. Traditional, easy, vector autoregressive process, and more involved continuous time processes. And you should be able to do quite a lot.
Yeah, I mean, then when we model the spatial properties, it boosts the performance, right?
Yeah.
The spatial height, I think there's no problem, but it's a temporal height. Temporal because.
Yeah, but in principle, you can do pretty much the same in time and in space. If you look at spatial temporal models, you could use some covariant structures, for instance, for how you merge space and time. And if you look at the environmetrics community, they have a lot of contribution. There are people in North Carolina, in Saudi Arabia, and so on. Marc Janton. So there are different types of models, so they can be separable or non-separable. If they are separable, you design some kind of covariant structure in space and one in time, and then the full space-time covariant structure comes from multiplication of the two. If it's non-separable, you cannot split the problem like that, but still you have functions that are extremely nice, that can cover a lot of nice processes. So, I mean, I could give you a few names. I think Tillman-Gneiting, Marc Janton, Montserrat Fuentes, a lady who is in North Carolina, who published extremely nice papers. There, the literature we have to look at is more for pollution. So these people have been looking at modeling wind, but more for transport of pollution. And they have very nice space-time models. So, yeah. Yes?
Okay. I like the fact that you're imposing those extra costs and, you know,
Thank you.
wind and solar. But like, I'm not sure how would they be responding towards this in the future, since we are far away from the markets of the future that you are predicting would be happening. So I'm not sure what would be happening towards the investment in, you know, renewable energy sector. So I was thinking maybe, like, that's good that they are paying for this and that provides some incentive for them to invest in battery technologies or demand response and so. But at the same time, maybe the market can consider some other costs, like the non-convex cost, or, you know, some other cost for those renewable energy generators.
Yeah.
So they are going to be paid some more amount, although they are paying some cost for these deviations from their forecast. So at the end, the amount of the cost they have will be reduced, or the amount of payment they
but okay, the thing is, we have to see it again as a game, right? So we have all the agents in the game. Some are the producers, some are the renewable producers, conventional producers, and consumers. Let's simplify. We don't look at the others. And let's say that the overall pot of money is constant, or the overall pot of cost is constant, right? Then what we care about is how we share, okay? So what we discussed today is not the fact that we put a new cost, is that this cost was already existing and the consumers were paying it, okay? And now we say, okay, no, we don't think it's very fair, so we want to redesign the game so that, because here, whatever now these guys are paying somehow, the consumer is not paying anymore, okay? So it's more of a point of who should be paying what. And this could be a very political discussion. It can be a very mathematical discussion. Here, Jean-Yves, when he contacted me originally, it was for that. It was to think of supporting new business models for demand response and storage. So you see, if we put this new cost, then it would incentivize that to invest in storage, because you could directly calculate how you would minimize this cost if you have a battery, or if you interact with a player that has a battery, all right? After that, I agree with you. I think we have to be a bit careful how we want to design the game, because if you're too rough on the wind farms, obviously people don't want to invest. But if you're unfair towards the consumers, I don't know if you have the same debate here, but in Europe, regularly in the main media, you have this thing, you know, our electricity bill is increasing, it's because of renewables. So is this fair also? I mean, it's true. I think in France and in Germany, they are making projections that are crazy. Like when we go to very high penetration, it's going to double, they say, the price for electricity. So, yeah. So it's very complicated. We are engineers or mathematicians. We are trying to think about these terms, fairness of the game, these three different type of attribution rules. But at the end of the day, it's political, I think, how we decide.
It's a very hard mathematical problem to come up with a price for both producers and consumers.
Yes.
Just from your experience, when you add this term, I mean, do you see them like using the forecast to minimize this term? Like, just play with the forecast to reduce the cost.
Yeah, but so there's three names here. There's Nicolas, Jean-Yves, and Mr. Tomosai. They were more into this game theoretical part of the strategic offering. And so, for instance, I'd say one of the main features we wanted is that you had no interest in being strategic. So what you're saying is that if I have to access to information, how can I write an optimization problem so that I lie a little bit or I twist the information to... So the way we design the system is in a way that you cannot benefit from that. So you have this incentive of being truthful, which normally is a feature you want for any mechanism design. We tried. I mean, we tried. We were thinking, you know, if we have a battery or if we are renewable alone, or this idea also of collusion, if I can make a coalition, can I have benefits? And then, so the point, if you go into detail, and we've not put it in the paper, it's actually still open, you have some metric. So this one mainly, is a metric where it's much more open to trying to be strategic, because it's, as I was showing, it's just this spike that counts, right? So you have an incentive to be a bit smart about this spike. This one, this inner product, has all the nice property. You can never get anything from trying to be strategic. That you put another asset, that you write an optimization problem just for your own, etc. So that's why this was my favorite metric because of this. These three don't have the right properties, and this one is the worst. But still, I think at the end of the day, I'm not sure the strategic behavior would be the worst issue for this cost here. I don't know. I think we need more work for that. The reason why we didn't invest further with this is because of what I was saying, you know, the fact that people in the real world were not really keen on implementing this kind of idea. We're saying, okay, what's the point? Are we going to go for a strand of research with all the nice strategic behavior and everything? Well, we know it's never going to happen for real. So let's wait for it happens, and then we invest more. And hopefully it will. I mean, yes?
They produce more than they predicted.
So we have this already. No, it's before. In this system, you're penalized in both ways. If you produce more than what you predict, or if you produce less than what you predict, you still have a loss. You have to think of it as an opportunity cost. If you produce more than what you predict, whatever you produce on top is going to be paid less than what you could have been paid if you had predicted well. So you have an opportunity cost. If you produce less than what you predict, you have a direct cost because you have to pay back somehow. But you always have a cost. And in Europe, it's quite complex because the costs are not asymmetric. It could be that the cost only exists on one side at a certain moment and not on the other side. As I was telling you, sometimes the system wants to tell you, okay, you made a mistake, but actually by chance it helped me, so you're not going to pay, right? And the incentives, I was talking about strategic behavior, that creates a lot of incentives. In the UK, Belgium, Germany, for instance, there's a set of incentives for certain behavior. And in Denmark, because we do different pricing, we have another set of incentives. And we have to think of that, because in terms of the system dynamics and how the players also will invest or behave, it's very strong, the impact. So.
Yeah, so since we're running out of time, I will stop at this point in terms of questions, but informally you can talk to Pierre after this talk, and also he's available for the rest of the day.
Yep.
So without further ado, thank you very much for coming, and thank you, Pierre, for the talk.
Thank you.